Okay, so we had left it at here, where we were discussing the how to define the variational derivative, and we have described it as if you can write down the change in the functional as an integral of this type, where you have some term multiplied by the small change in function that you have, then the variational derivative essentially is defined as the integral itself, okay, which is dou f by dou y minus dou by dou x of dou y prime, where y prime is dou y by dou x. Okay, clear? Okay. Now, and we said we are now going to be looking into how to get a visualization of this fact, and I said we will resort to a little bit of discrete mathematical activity. So, how does the discrete mathematical activity look? You have I(y) of x defined as this integral, but now think about it. Y of x is not a continuous function, but I have y of x defined at discrete points. Okay, so from x1 to x2, think of it, I am dividing the interval into multiple intervals as fine as you please, and at each of those points I have defined the value of y. So instead of a continuous description y of x, I have a set y1, y2, y3, y1 until yn, depending on how many set points I have divided to. So if I do that, it allows me to do certain things. I can take a discrete derivative. I can define v dy by dx as a finite difference of, if I want to compute it at a given point I can find that yi plus 1 minus yi by that. I can define it. This is well before this. So this integral, I can then transform it to a sum, where I'm saying that I'm writing this sum over as many intervals I have broken it into, n is equal to 1 to n. Each of them is written as yi at each position times the derivative at yi plus 1. So that equivalence is clear. I am transforming this integral into a discrete sum, and this will approach this as I tend to infinity. Right? Number of integrals. The reason I am doing this is because now I can think of changing locally the function at a given point. And what does locally the function mean? Let's say I choose the localized change at a given point y I. I will just change the value of yi in this discrete set by a small value and ask myself, because of that, what change happened into infinity. Okay? So I am going to write this down as an in. It's just the infinite sum of the number of, not infinite, finite sum of. So because this is going to involve all the values y1 to yn, so from this you get an integral sum, which is a function of n variables, the variables being the values of y at the n discrete. Clear? Okay, so now I can think of doing this. I can think of partial derivatives, and now I'm precisely doing that. I have that function, which is the sum of multiple variables, y1 to yn, and I'm changing the value of just one point yi, right? And asking the question, what change does it do to my overall sum, which is I, right? And this I can do now, because I have precisely a function of multiple variables, right? But now, if I want to compute this from the previous description over here, right? This is my description, and I want to compute this at a given point by k, for example. Can you tell me whether this makes sense to you? This expression over here. If I start from this expression for the f, that is, you have f at yi plus 1 minus yi, right? I am doing the summation from I equal to 1 to n, and I am now locally doing dou I by dou yk, okay, at a given point yk. So does this make sense to you? So, there are two terms where yk will be there. Okay? Two sums, two partial sums where the yk will be there. So, if yk to be yk plus 1 minus yk, right? But you also have yk minus 1. Okay, two terms where yk will be present. The difference. And one term where yk will be present here. Okay? Now with that, does this make sense to you? Yk plus 1? It depends on where you put the thing. So this is the derivative at yi. So this is the derivative at yi. Then you define the derivative at yi to be yk plus 1. But that's derivative at yi. And derivative at yk minus 1 will be yk minus 1. So you have derivative at yk and derivative at yk minus 1 coming in. Because this is derivative at yk or yi. This one. So this is yk plus 1, let's say k, yk plus 1 minus yk. So this is derivative at yk. Okay? Similarly, there will be two terms over here. Yk plus 1 minus yk. Right? And yk, right? This is derivative at yk. This is derivative at yk minus 1. Okay? So, does this make sense? When it is appearing here, you have 1 by y dx by dy. Yk will be positive, yk minus 1. And here it will come yk plus 1 minus yk. So it will come to negative sign. Alright? So if you put the two together, you essentially have what is the difference between this and this? If I do 1 by delta x of rho f by delta x, rho f by rho y prime at yk minus 1 minus yk. So essentially, yk is a dependent function of x. Okay? So it will just do by dou x of rho f by rho y prime. Right? If I take multiple intervals, and essentially my partial derivative becomes this times delta x. Alright? So compare this. This is what your variational derivative was. This is what your variational derivative was at yi. If I compare the two expressions, I essentially have that the variational derivative of I by y is essentially limit delta x tends to 0 because as fine as you please, dou I by 1 by delta x. So if you take delta x this side, right? That is your expression. But what is this? This is a change in the integral. What is this? It is this. Okay? You change locally the function a bit. This is the change in area that you did. Right? Because of this change in area, you are asking the question, what is the change in the integral y? I. Not y, I. Okay? And that's how you would visualize the variational derivative. Okay? You're doing a small change in the function, which is causing a small change in the area function that is part of the integral. And because of that small change in area, we're asking the question, what is the change in the actual functional that you started with where y is? Alright? That's how you would picturize the variational derivative. Alright? And if you think about it, that's the only way to visualize it. Because you are locally changing a function, it cannot be a value. It has to be some sort of an area of this thing. Right? So when you're talking about integration of the final change. Okay? So with that, we have a new operator at our hand, which is I'm going to call this as some small f, so that this is what you have. Alright? This is what we have just derived. Alright? Our new derivative. Now, this is in 1D. How would it look in 3D? Just a quick question, just an instinctive question. What does your instinct tell you? So it's dou by dou x of dou f by dou p by dou x. Okay? So del log. Okay? Because this process will be repeated in every direction. Okay? So dou by dou y, dou f by dou y prime and so on. Okay? So we essentially have as this in 3D would be minus and to talk about gradients, we'll introduce this as the function. So you have the variational derivative defined as this operator. So if I'm going to talk about an operator, then that's all. So this is your variational derivative. All right? Just go back here. So you have y prime. So let's say you have other dimensions present. You have y prime x, y prime y, and y prime z. So when you do this is just a repetitive thing that you will be doing for each of the dimensions. You come to the same thing. Variation is any independently. Yes, because it is a first order derivative. Okay, good. So we have learned a new operator. The consequence of doing a new operator now is that this operator is what I will now be using, because understand what the question is. I have a functional, right? I want to write the evolution equation of this functional with a new machinery which I have just derived. And the idea is the following, that I want to come to a steady state of the problem. So my partial differential equation should be essentially a function which minimizes this function. Okay? Now what does minimizing mean? It essentially means it is a function which leads to the lowest integral, the functional of the value. Okay, okay, so if that is my aim, I'm going to arbitrarily write down an evolution law of the type of this type, right? And this is the first type of motion that we will study, which is the Lenzman type of dynamics. Okay, I'm writing a functional. I have defined my variational derivative, and I'm saying that my phi will evolve in a way that it does this when the variational derivative. Okay, the reason I'm writing it this way will become clear in a few moments. It is essentially such that my functional reduces its value for every time step of integration that I do. Okay, now that is some proof that I will present to you in a few slides. But this is essentially what this first type of dynamics that we will. Okay, now given this is so, can somebody populate what this evolution equation will be, given that is the functional and this is the operator? So I'm writing it this way. This is your functional, this is your operator. Can you evaluate that for me? What will this partial differential equation be? Okay, so I'll help you out here first. This is your f, small f, right? Dou by dou phi. Will this term contribute to dou by dou phi? Huh? Will it contribute? No, yes. This one? Huh? Yeah, I'm asking. So this will not contribute because it's a function of only phi prime. Okay? So your derivative with respect to y and y prime are two different, as you saw in the derivation. You're taking a derivative with respect to dou f by dou y and dou f by dou y prime. They are two different derivatives. This is a function of y prime. So dou f by dou p is 0. Okay, so this will not contribute. What about this? This is a function of p, so dou by dou p will contribute. Right? What about this? Dou by dou grad phi. This contributes, this one will not contribute. What is dou by dou grad phi of this term? Just take the grad 2 kappa grad phi. Okay? So it's a very simple math. So you have which is dou by dou phi of this term minus all right, makes sense. And if you compare it to some moments ago, this is the equation where we started from. Okay, this is what we wanted to derive. We wanted to start from here. We want that equation that we modified such that we get a nice diffuse interface profile. Now I'm writing down this equation as a consequence of derivation of from a functional to a new machinery that I have introduced. Okay. The question therefore is, if now dt phi is 0, does this also correspond to the minimum of this functional? Because then I have a thermodynamic means of evolving this function. That is, when I am at equilibrium. The function which gives me the equilibrium also minimizes a thermodynamic function that I started with. I can populate this with as much energetic terms as the system has, and the minimum of that would correspond to equilibrium, which would mean that the time derivative at that state will be zero. Right? So, if dTp is zero, this certainly has a solution in 1D, which you just saw is your tan hyperbolic profile. The only thing to remaining to be proved is that at each time step of integration, this is a monotonically decreasing function. If you do it this way. If you prove that, then once it has become zero, it is essentially going to be the equilibrium state. Alright? So how do we go about proving this? The next part here. I didn't know how to get out of the full screen. No, not the escape. This has become full screen mode. Huh? F11. The issue is that I'm not able to select control key. So let's go here. So this is something that we have derived. And now we'll go into some of the properties of this function. So just 1 second. Okay, so what I want to do is the following. I want to create the time derivative of this function. Okay, this is what I want to do. And I'm going to be doing that. Remember, this function is changing because of the variable c. Right? So I'm going to write this down as alright. I'm going to write it down like this. What does this mean? This is the change in the functional at a given rate of change of the functional as a function of time. How will you evaluate that? Go to every c point in the domain, calculate the variational derivative of phi, and the phi is changing at that position corresponding to d phi by dt. And you integrate that, you will get the total change in the function of time. Right? That's what it is. So it's easy to see if you do dphi by dt over here, replace it with minus m delta s by delta p. What it becomes is minus m have this, and as a consequence, what will be the value? This is always positive. This is a positive constant. Therefore, this value will always be negative. Okay? And it also says that when this vanishes, this also vanishes. That means when this derivative becomes 0, variational derivative becomes 0, your steady state is also achieved. And this is 0, and since it is always coming down with time, necessarily this is the minimum of the function. Right? So, by evaluating the function in this way and constructing the partial differential equation in this manner, you essentially evolve phi such that the functional necessarily reduces with time at each time step of the integration, and when you instead, you essentially come to the situation that the variation derivative with respect to phi vanishes corresponding to the equilibrium state. Okay, so the phi corresponding to which you will have this equilibrium state is essentially the equilibrium steady state function. All right. So, and that particular profile has certain properties. So let's say the solution of this equation when this becomes 0, when the variation derivative vanishes, it forms P equilibrium. When do you put this value back into this function, right? At steady state, and since the steady state actually appears only in 1D, in other dimensions you will not have a steady state arising out of this equation without a gravity force. We'll see that later courses, but presently you take it from me that this particular state of the equation or functional has an equilibrium only in 1D. Okay, which means that if I write this down in 1D, will be this, and the state at which this the value of the functional when phi is corresponding to the minimum of this functional has some special properties. What are those special properties? First you can follow. So remember, at the equilibrium state, the variational derivative is 0, right? And variational derivative of this you just computed is, I'm going to term this equation what you like here. Which symbol do you like? Huh? Sigma. Huh? I'm going to write this entire thing as W. Alright? This entire thing I'm going to write as W. So, essentially what you have is that the variational derivative vanishes, which means okay, d by dx of k dp by dx, but kappa is constant, so you have kappa d square by dx. Alright? So this is 0, which means that is equal to dw by dt How would you integrate this? Fantastic. Remember I told you you were going to use this function, use this thing a lot of times. And I'm going to integrate it from minus infinity, which is the left side of the interface, to 5. Right? 5. So, what is this integral? That you just computed. Kappa. Right? And this one is just W of 5. Right? W of 5. Remember minus infinity, it is P1. Right? So, at P1, W is P squared into 1 minus P squared. So, P at 1 is 0. Okay, W at minus infinity is 0. So, you have this equal to W of P, and I erase the functional for some reason. This is the condition that at equilibrium you satisfy, right? And at that same condition, it implies that this term in the functional becomes identically equal to this term in the functional for all values of p. Okay? This is the state when you are at equilibrium. Means for the equilibrium function phi, right? You put it back into the functional, it will satisfy this property. Because it satisfies this property, the value of the functional can be written as 2 times sorry. Because this is equal to this, you can write it as 2 times kappa dt by dx the whole square, or you can also write down as okay. Both are equivalent. Correct? Now, who can compute for me if I define W of P as some W times P squared into 1 minus P squared, right? If I define it this way, can you compute for me what this will be? Or this, both are equivalent. I'm going through this machinery because this machinery is going something that I will be using for doing more complicated things during the asymptotics. Okay, so I'm getting you acclimatized with this because this we will be repeatedly using. So 2 kappa dp by dx the whole square dx. I have dp by dx. dp by dx is root of 2w by k into this. Okay, that we know. So this guy over here, I can write down as at minus infinity, it's minus 1. Sorry, 1. Does that make sense to you? I've converted this integral to this over here. It's something very simple. I'm just expanding dp by dx times dp by dx, and 1 over dp by dx and transforming to dp. Okay, so essentially converting the from a variable in x to a variable in phi, which I can immediately evaluate. Okay, you can also alternatively put the phi that you derive, tan hyperbolic, take the derivative of the tan hyperbolic, square it, and take the integral in x. Equivalently, this is something that you can do. Why is this easy? Because I have dphi by dx already derived over here. It is from here, dphi by dx will be equal to root of minus, because you are going from 1 to 0, phi into 1 minus 2. Alright? So, you have dp by dx as minus root of w by k, phi into 1 minus p. So, what will be the value? Huh? What will be the value? So, you have root kappa here times root w, so you will have, right, 0 minus, so this minus will essentially invert this integral from 0 to 1. Okay, and you will have p into 1 minus p dphi, right? Correct? So p into 1 minus p dphi will be p squared by 2 minus p squared by 3, 0 to 1, 1 by 2 minus 1 by 3. You will have okay, so this is the value of the functional at equilibrium. That means when you put the equilibrium state phi into the functional, this is the value of the functional. Okay, and this functional, this value, because it's in the equilibrium state, is referred to as the interfacial energy of the problem. Okay, so this is what I'm going to refer to as sigma. It's the equilibrium property of the problem or the system, and it is at the state when the variational derivative of the functional vanishes with respect to phi, and the value of the function at that position is the minimum of the system, which is the interfacial energy. Notice what contributes to the interfacial energy. Two terms. One is the coefficient of the square gradient term that is there over here, and one that is the proportionality factor, which determines how high this barrier function. Okay, how does this function look between 0 to 1? It looks like this. Okay, from 0 to 1, and what this W does is essentially scale this height of this barrier. So your interfacial energy depends on two terms. One is the square gradient term, kappa. One is this barrier height, both of which can be used to modulate what your interfacial energy of the problem is. Okay, and it's a root of this. Remember, square root of the product of the coefficients. All right. So this is one property of such a dynamical system that we have created. That means if you derive the dynamics from a functional, writing down the electron dynamics, solving it to the steady state, and determining the energetics of the problem, you have the equilibrium being defined by this, and this is a physical property of the system, which is the interfacial energy or a surface energy, depending on the state. All right, what is something else that you can create? So I will leave it as an exercise to prove that if you were to do this integration as well, you will get the same thing. Okay? Tell you why. To convert the same way, convert this integral in x to an integral in phi by writing it as dx by dphi times dphi. And dx by dphi is something that you can again derive because it is the inverse of dphi by dx. And you can basically come back to the same integral. Alright? So that's not a surprise. You will be getting the same value. Okay. There is something else that you can derive, and that is to do with how diffuse is your interface. So you have created your function, right? It is your equilibrium function. Now, what we have decided is, if you put this function back into the, what is the value of the energy? But additionally, how do you control how diffuse it is? Whether it is diffuse like this or diffuse narrowly, what decides that state of the system? So that also can be derived directly from this, right? We have dP by dx giving rise to minus so what you can do is to say that and you integrate from x negative 1 to 0 and the resultant is the interface width. Okay, lambda. Right? We integrate from the value from where phi is equal to 1 to the value where phi equal to 0. The length is the interface width, which is the length over which you are diffuse. Right? So what is this integral? We did this integral a little bit time back. So this is just log of phi over 1 minus phi. And you will realize that I cannot integrate from 1 to 0 because the logarithm becomes undefined. So what you do is to basically define that you are going to be computing your diffuse interface width within certain limits, 0.1 to 0.9, in which case you can essentially compute this integral. Right? But that essentially will give you lambda. And notice that this is just a factor. This is just some numerical value. But lambda itself is going to be this. Lambda itself will be proportional to root of k by w into some number, which is the integral of this. Okay? So you have sigma, which is proportional to root k times w, and lambda, which is the interface width, proportional to root of k by w. Okay? Or in other words, we have sigma times lambda, and sigma times lambda will be something proportional to k, and sigma by lambda w. So another way of writing this equation is to say that the functional can be written as sigma times lambda times square plus okay. The reason you do this is the material property is directly visible here, which is surface energy, and lambda is something that you want to control in your simulation. So both of these parameters directly come into the function. Okay, they are also there in the other one, but then it is more direct evaluation over here. That makes it slightly easier to use. But both are equivalent. The other way of writing the function in terms of kappa and w and sigma and lambda. But the two important properties essentially remain that we have 2 degrees of freedom with respect to the choice of the phase field parameters. One that influences the interfacial energy, and second that controls the interface width. Right? If you want to change the interface width, so if you want to change the interfacial energy while keeping lambda constant, right, you will have to change both kappa and w, right, by the same factor. Good. Any doubts with the electron equation? Clear? Okay. So by the way, this relation is also called the equipartitioning relation. Essentially, because you are partitioning the total energy of the functional between the square gradient and the potential term, right? At equilibrium. Right? All right. So let's say now I do something to my functional. This is the functional that we started from, right? Where the sum we started with the functional. And remember, I said that P is an indicator function. Indicator function means it is telling that it is showing me parts of the domain where one phase is present, another part of the domain where the phase is not present. Alright? But that's all it is doing. And the question is, the same set of functional, let's say I write it down with a different sort of variable. Where now, instead of P, I use C. Okay? So P is an indicator function, whereas C is the composition. Okay? Both are essentially trying to do the same thing, demarcating regions where a particular phase is present. Here it is doing by compositional differences. Here it is possibly doing it by just an indication. Okay? But I am, in principle, allowed to write down both types of functionals if I am going to start for a system. The question is, for this part of functional, I said that I evolved my system using an arbitrary law of this type, which I refer to as the Allen-Kahn equation, right? Can I do that for this? Can I do the same for this? How many say yes? Okay. How many say no? Rest of you say no. The precipitation varies. Can we do what sort of dynamic could we write down? Can we do this? No? Well, we can? Huh? Louder, louder. Can be done? Without minus sign. Then the thing will increase, no? Value of the function will increase with time. So how many, whoever is saying no, why cannot be done, it be done? What is that? Both are very between 0 and 1. Yes. So the difference between the two ways of writing the thing is the difference in the order parameters that I am using over here. Okay? Here it's just an indicator function. An arbitrary function I am creating. Okay? Whereas here it is the composition. So if it's a composition, integral CdV is constant for every step of the integration. No mass goes or leaves the system. So my evolution law must conform such that must conform to this constraint. All right. So what should I do? How do I conform to this constraint? Yes, you can add constant equation. Okay, I will. You can derive it that way, but the easier way to do it is the following. This is a conservation equation, right? Any conservation equation, how do you write it? If you were to write the conservation equation for a variable c, how would it look? What's the term here? Huh? Okay, divergence of flux that leads to accumulation of mass. All right, we're clear about that. Now the question is, can I solve this equation? I can't, because I need to relate J with C, right? How do I relate J with C? Yes, how? What is the constitutive relation I use? Who is saying this? You are. Is that okay? I am contesting that thing is wrong. Okay? That's incorrect or partially correct. Right? Why am I saying so? Well, why should I invoke chemical potentials at all? Source terms? No, source terms are fine, but tell me what is the fallacy of this equation? Let me guide you this. Almost everybody understands phase diagrams, right? Anybody not understanding phase diagrams? Phase diagrams? So let's say, again, you like solidification or precipitation? Huh? Okay. So we'll draw solidification type of phase diagram, right? So solidification can happen. Let's say we are at temperature over here. This phase has a composition C alpha, and this phase has a composition C beta. Right? Yeah. And now what we do is the following. We create a thought experiment where we put alpha and beta in contact. Right? Which means this is at C alpha and this is at C beta. Right? So what is the composition profile across this? Okay. Is that all right? So, if you follow this equation, do you expect mass flux across the interface? How many say yes? Rest of you say no. Why? What's the gradient? No. There's a gradient of C. You must have mass flux across the interface. If you have mass flux across the interface, atoms will move from here to here. There will be repartitioning. But you're at equilibrium, no? At this temperature, if you put this composition of alpha and this composition of beta, nothing should happen at the interface. It should be at equilibrium. But you're moving. So what is the problem? Huh? No, the net flux will be going from here to here, no? but you're at equilibrium. So what is the problem? But you're at equilibrium. You cannot move. This equation doesn't know the phase diagram, but it must know the phase diagram. Must know. Then otherwise it becomes thermodynamic inconsistent. No. So because it doesn't know the phase diagram, the correct equation has to be m grad v. Okay, where m is the mobility, right? Times grad v. Because if I do this way, at C, if I write down if I plot the chemical potential across the interface, the flat line, gradient mu is 0, the system must be at equilibrium, and there must therefore no flux circle. Okay, everything is fine, right? So the problem is you cannot use the fixed equation when there is a discontinuity of a phase. You can only use it when the phase is homogeneous. Okay, if there is a discontinuous boundary, you will have to solve on each side of the equation the diffusion equation and apply the boundary conditions that we had been talking about before for the semi-superconductor. Right? Okay, so with that we have etc is equal to minus del dot m grad mu. Okay? Can we solve the problem? No, can we solve the problem even if m is constant or not constant? Doesn't really matter. Can I solve the problem? I want to evolve C. Can I solve this partial differential equation? Guys, don't go to sleep right now. Or you forget about minus. Achuk is doing slip catches. I have to express mu, no? Otherwise I can't solve. So what is mu? What is mu? So we come to the very important definition of a very important thing. Change in free energy per change in composition. This is mu. No, this is not mu. This is F. This is free energy. This is not mu. We are coming to that. But F itself is not mu. Yes, but why? Let's go to the fundamental difference. So let's say all of you understand G versus X. G versus X. Anando? Long time back. But do you remember? Remember your comprehensive days? Let's say this is your nice looking G, right? Who can tell me what is dou T by dou X? Ten to 10, guys. Huh? Huh? You get a cheeky. Is it this? Huh? Is this? Huh? Is this the chemical potential? That's not the chemical potential. No? What is the chemical potential? Is the chemical potential? Huh? Okay, but you just said no. Derivative. Derivative is this, no. Huh? Which one should I put? This one or this one? Why should I do BB minus B? No, mu B minus mu A is that slope. But why should I do the slope? You understand? Why should I do the slope and not the chemical potential? Chemical potential is equal, no? Both sides of the interface. Huh. You don't need double. No, this is a fundamental thing. There's nothing to do with this fellow. So, when you're having a particular type of diffusion meaning, let's say you have a binary alloy. You have consistent of A and you have consisting of B, right? And you have a substitutional diffusion happening. It means the only way A can go from one side to the other is only by a motion like this. Which means, energetically, you must not only be talking about the change when you make one change in atom A, but replace it with atom B. So the energy you must be looking for is precisely free energy per atom of A minus free energy per atom of B. So that is the change that you're going to be doing when you're going to be doing the diffusion. So you're talking about free energy per atom of A minus free energy per atom of B. Free energy per atom of A implies the chemical potential of A minus chemical potential of B, which is mu A minus mu B for substitutional diffusion, which gives you the slope of the line, which is dou G by dou X. Okay? If you were to be doing some other sort of diffusion, like interstitial diffusion, where you are not doing this exchange, you are just dependent on the chemical potential of A. Okay? The gradient of chemical potential of A will define the dynamics of how A moves, not the difference. So this is a critical term, critical difference. You must be worried about this when you are looking at the mechanism of diffusion plays a role in writing the constitutive equation that you start from. So this is also called by different names. It's called the effective chemical potential, or sometimes also referred to as the diffusion diffusion. Okay? Because effectively, what is the system energetics that defines the motion of the atom is what we want to use for these plants. So therefore, I'm going to use this mu in the effective sense of the word, but then can I compute it dou G by dou X here? Will it be dou G by dou X? F and G are interchangeable here. Should it be dou F by dou C or something else? Remember, here we just don't have a local description of the free energy. You have a non-local term setting over here, which is dependent on the gradient of C. Alright? So when you do the change, the functional is changing because of both this changing as well as this changing. Okay? So a variational derivative is because of, or rather the free energy change that is happening can happen on account of the change in the gradient as well as change of the C, value of C at given. Okay? So the operator you should be using therefore, when you have a term like this in the functional, is not the partial derivative, but the variational derivative is 0. And that's why you have mu is equal to delta f by delta c. Alright? And this you all know how to break now. So we will write down so you have so mu is the variational derivative delta f by delta c. Delta f by delta c I will write down immediately as what? Everybody agrees? Oh, not C. Everybody agrees? Clear? So if you put this back into this equation, you would get dou T by dou C is equal to N alright? So this is your, that was a Alan Kahn equation which I wrote down earlier. This is the Kahn-Hilliard equation. Hilliard equation. Remember now you have, instead of a del square, you will have effectively del square. So you have a del power 4 term. So instead of a harmonic operator, you have a biharmonic operator. Right? So this is therefore fundamentally different from the Alan Kahn equation, in the sense that evolution dynamics will be different and how composition evolves in time, just because it's evolved from a conservation level. Alright? Any questions? It's because of the evolution of how I have defined the evolution law. Del.J. I am writing flux. Divergence of the flux is what defines my evolution. Nature, it is conservation. Flux is what? Divergence of fluxes, flux coming in, flux going out, leads to increase of composition. So divergence. Right? So if you do it that way, the composition is conserved, and because the constitutive relation relating the flux to the chemical potential is minus m grad mu, we end up with this. No, Alan Kahn is not conservative. It doesn't have the constraint, no. Okay. So now what is the question left? The question left is, yes, you wrote down this evolution equation, but does this minimize the free energy function? Right? Because this is a different dynamics, no? But it still, does it still retain that property that the free energy functional reduces with time? Okay, so let's look at that. your Planck-Gauss equation. So we'll do the same thing. So we'll write down the okay. But dc by dt, we'll do it in 1D because it's easier to see things. Otherwise, we'll have to invoke Green's function and so on. Okay. So if you put this guy here, you have mu. This is mu, right? Times all right. This is what we have. And then what we will do is to do partial integration. Okay. So we will differentiate this guy, integrate this guy. Right? Differentiate this, integrate this. So what you will have is mu j, which is this is j. Okay. Minus of that doesn't really matter. So this is mu j that will come out of the integration plus dv by dx times j. dv by dx is, or rather j is minus m grad mu, right? That is dv by dx. So essentially what we will get is minus of n times dv by dx the whole square. Okay, and here this is a boundary term, right? Mu times j at the boundary, right? Typically, if no mass is entering the system, you are not adding any energy to the system. So this is actually zero. Okay, so in the case where it's a closed box, j is at the boundary is precisely zero, so this term drops off. So your energy for the system is precisely determined by what is happening in the bulk, and it will be directly this. This is minus n times dv by dx the whole square. That is deciding the rate of change of your functional. So when does this become zero? When dv by dx vanishes. And dv by dx vanishes because at equilibrium mu is essentially uniform all across the system. So dv by dx does indeed vanish, and therefore the system does equilibrium at that point. Not only that, because this is positive, this also ensures that your energy of the functional or the free energy functional goes down with time for every step of it. Right? So look at the fun of the matter. The Lorentz equation as well as the Kahn-Elliott equation both ensure that your free energy functional is reducing with time, except that the dynamics is different. Okay, the dynamics is different, and that's essentially important to know. Right? So what is left? What is left is the equilibrium will attain when chemical potential becomes uniform in the system. Right? So therefore, can we derive the condition for equilibrium, that is C of x such that the chemical potential becomes uniform in the problem. Alright? So who will attempt to do that problem? Precipitate phase. So dt by dc, as we all agree, the function will come to its rest state when mu becomes uniform all through, right? So mu will become uniform all through when this is mu, right? What is inside the brackets? So mu is uniform implies minus is equal to uniform. What does uniform imply? Is the equilibrium value the problem. Now remember, I referred to this guy as the slope, dg by dx or df by dc, all right, and not the chemical potential, rather than the effective chemical potential, which means this is if these are the two parallel curves to alpha and beta. I am referring to the condition where a certain state like this is admissible. All right? Because here the two curves will be. So let's search for this condition. This is one equation that it must satisfy. That is, the mu is uniform. Can we integrate this in 1D? And I said this as again an equilibrium only in 1D, not in elsewhere. So I will write it as this way. So can we integrate? How do we integrate this? Very good. So, as I said, this is the same fit that we will be applying almost all through. Okay. Okay. Now, so what is the integral of this? This is W of C, right? Integrated from some value in the bulk, which is C alpha. Let's say we have a situation over here where on the left is alpha, on the right is beta. So C alpha to some value C minus again some value in the alpha, some value x, kappa dc by dx whole square, because dc by dx vanishes here, the uniform part, and you have over here equal to mu equilibrium. This is C minus C alpha, right? Okay, so you have omega of C evaluated this way. So you have omega of C minus omega of C alpha minus K dc by dx whole square times equal to mu equilibrium. Okay, is that all right? Any confusion? He looks confused. Be straight. Yeah? Are you confused? Partially confused. Fully confused. Okay, so how to make sense of this? Let me deal in. That's the condition at equilibrium. Okay. How do we make sense of this thermodynamically? Remember, I have denoted the slope of this line as mu equilibrium. Let's say I integrate this from minus infinity to x is what I've integrated. No? Let's say I integrated from minus infinity to plus infinity. So this term will vanish, right? dc by dx whole square. Left side is flat, right side is flat. So this term will vanish. So what I'll be left with? This equation, right? Omega of c minus omega c alpha, rather omega of c beta minus omega of c alpha, mu equilibrium c beta minus c alpha equal to 0, right? We get a condition which is relating omega of w of c alpha minus and w of c beta. What is that condition? Let me write down more precisely. If I integrate from c alpha to c beta, this is the condition that will come if I integrate from minus infinity to plus infinity. What is this? Huh? Somebody uttered something. Exactly. So, what is W of C alpha minus mu equilibrium C alpha? It is the intercept. The intercepts are equal along with the slope, which essentially means this much corresponds to the common tangent. Right? So again, the two conditions for equilibrium. One, that you got out of the condition that mu is uniform, that gives you that the slopes must be equal. But if you integrate that equation, you get a second condition for equilibrium, that along with the slopes being equal, they must also be on the same line. That means the intercepts must lie on the same line, and therefore they must be on the common tangent. So C alpha and C beta have to be those compositions which correspond to the common tangent construction between alpha and beta for the equilibrium fluids. This you know out of thermodynamics. This you know out of thermodynamics. It comes out of your calculation. Right? Now let's proceed here. This is somewhere in between the integration. So omega of c minus omega of c alpha is what your equilibrium condition will look for any point in the domain. Look at this equation. Remember, if I put w of c is equal to this function that we had before, right? Where does the common tangent lie for this equation? Oh, sorry, c. Where does the common tangent lie? Common tangent is right. This is common tangent, right? This is c square into 1 minus c square. The common tangent is this. It means mu equilibrium is 0. Also, if you take the intercept, that is also 0. Okay. So what you get? You essentially get to a situation that both your WC and the mu equilibrium are both 0. right? So what are we left with? W of C. So this is the equilibrium condition. W of C is equal to K dc by dc square, dc by dx square. But look at this equation. If I replace C by Phi, it is exactly the same condition that you got from the Elenchon equation. Okay, it's exactly the same equation, same type of equation, equation that you derived, right? And therefore, the solution that you will derive for the equilibrium composition field will be exactly the same as what you derived for the Elenchon equation. You get an hyperbolic of this. But remember, the dynamics is different. The way you will reach from the initial state to the final state is different. It still reduces the time derivative. I mean, the energy will reduce with time in a different way. Your final states will also be similar. Not similar, exactly the same. Okay? And this will happen only when your W of C is looking like this. That is for the situation where mu equilibrium is 0 and W of C alpha is 0, as it is the case over here. This is typically not assured to be the case, as you have over here. You are free to have your free energy to be as arbitrary as this, which means your moment tangent, the mu equilibrium need not be 0. And so does your intercept not have to be 0. In which case, your equipartitioning relation will take the more generic form, which is this. Okay, instead of the simplified form which comes out. Right? So there is a subtle difference in between what the dynamics will be. Alright? What is this energy? Can somebody point to me on this graph? Can you point out to me what this term is for W looking like this? Huh? Right from the common tangent. Like this. Okay, why? You have W of C. This is the equation of the straight line corresponding to the common tangent. Okay, and therefore, this is directly the difference between W of C and line. That is your. This is therefore also referred to as the interfacial, the term leading to the interface axis between alpha and beta. This directly contributes to the interfacial. Okay? And this is therefore the equipartitioning relation between the square gradient term and the interfacial energy term, as you had in the Elenchon equation. Except that you replace this with this term for the equipartitioning. Okay? Good. So because if you choose W of C as like this, and since this remains the same, the surface energy, the interface profile, the equilibrium interface P function will all be the same, right? But it will not be the same if it is an arbitrary function of the same, right? So this is a subtle difference you must keep in mind for this. Okay, so this is essentially the two types of equations or two types of dynamical ways you can write down evolution equations in the problem, right? One, the Elenchon dynamics, which is a phenomenological type of dynamics. I'm just writing down dp5 is like a steepest gradient type of minimization where I'm just following the slope of where the function is reducing, right? Similar to that. And the second is the conservation law. I'm getting my conservation evolution equation. All right?